Hello everyone. This video is brought to you by the Atılım University OpenCourseware project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and the video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem in Chapter 10. For convenience, let me show you the analogy between the linear motion and rotational motion. As you remember from the discussions in motion along a straight line, linear variables can be listed as position, displacement, average velocity, instantaneous velocity, average acceleration, and instantaneous acceleration. And their units are shown in SI units in this picture. However, in the second column, you see the variables in the rotational motion, and they are listed correspondingly to the linear variables in the first column. For example, angle or angular position theta is corresponding to the linear position x, and it has units of radians in SI unit system. Next, delta theta is the change in the angular position, or it is the change in angle. Other rotational variables are average angular velocity, instantaneous angular velocity or angular speed, average angular acceleration, and instantaneous angular acceleration. Generally, in this chapter, we don't use the vector notation for the rotational variables. Okay, that's all for the analogy between the linear variables and the rotational variables. As a next topic, let's establish the analogy between the motion with constant linear acceleration and rotation with constant angular acceleration, which is shown in this table. Angular position or angle is found by this formula, where theta 0 is the initial angle and omega 0 is the initial angular speed. Also, alpha is the constant angular acceleration. Second, angular speed is found by this formula, or if we are not given the time during the motion, we use this formula to find angular speed. Okay, let's have a look at the last analogy. First, corresponding to the mass in linear motion, we have moment of inertia shown by I in angular motion. And the Newton's second law in linear motion, shown by this formula, has this form in angular motion, where tau is torque, I is the moment of inertia, and alpha is the angular acceleration. As you know, torque, shown by tau, is a vector and calculated by this formula, R cross F. And rotational kinetic energy is 1 over 2 I times omega squared. And rotational work is torque times delta theta, corresponding to the linear momentum in linear motion. We have angular momentum in angular motion, and it has the magnitude I times omega, and also, since it is a vector, it is calculated as R cross P. Finally, we have the total linear momentum in linear motion, which is calculated by the sum of the individual linear momenta of the single particles, and we have the total angular momentum in angular motion, which is calculated by the sum of the angular momenta of the individual particles. Very good. Now it is time to discuss the problem. A rotating disk completes 26 revolutions as it slows with constant acceleration from an angular speed of 2.2 radians per second to a complete stop. In part A, find its angular acceleration. In part B, find the time required for it to come to rest. And in part C, find the time required for it to complete the first half of the 26 revolutions. In the first part of the solution, we write the given numerical values in SI units. Since revolution is not an SI unit, we have to convert it into radians as 52 pi radians. Initial angular speed, say omega 0, is given by 2.2 radians per second, which is already in SI unit. And the final angular speed, shown by omega, is given as 0. In part A, to find the angular acceleration, we use this formula, which does not contain time explicitly. Therefore, omega squared, where omega is the final velocity, which is given as 0, is equal to omega 0 squared plus 2 times alpha times theta. And we find the formula for angular acceleration as alpha equals minus omega 0 squared over 2 times theta. If we substitute the corresponding numerical values into this equation as 2.2 radians per second squared over 2 times 52 pi radians. If we calculate, you obtain minus 1.4814 times 10 to the power minus 2 radians per second squared, which is approximately minus 1.48 times 10 to the power minus 2 radians per second squared. Remember that intermediate results are written in 5 digits and the final results are written in 3 digits. In part B, we use this formula to find the time required for the rotating disk to come to rest. Here, the final angular speed is 0. Then we obtain the formula of time as t equals minus omega 0 over alpha. Here, we use the given value for the initial angular speed, which is 2.2 radians per second, and we use the result in part A for the angular acceleration as minus 1.4814 times 10 to the power minus 2 radians per second squared. Finally, we obtain the time required for the rotating disk to come to rest as approximately 149 seconds. In part C, we find the time required for the rotating disk to complete the first half of the 26 revolutions, that is 13 revolutions. And in SI units, it is 26 pi radians. We use this formula to find the time. Since this is the second order equation in t, we arrange this formula as 1 over 2 alpha times t prime squared plus omega 0 times t prime minus theta prime which is equal to 0. If you solve this second order problem, you find t prime equals minus omega 0 plus minus square root of omega 0 squared minus 4 times 1 over 2 alpha times minus theta prime, and the whole thing is divided by 2 times 1 over 2 alpha. Or simply t prime equals 1 over alpha times minus omega 0 plus minus square root of omega 0 squared plus 2 times alpha times theta prime. And put the numerical values corresponding to the right places in this equation as this. And if you calculate, you obtain two results for time, which are 43.5 seconds or 254 seconds. Here the correct answer is 43.5 seconds. Okay, this is the end of the solution of this problem. Thank you for your attention and see you in the next video.